Hydroelectricity is the term referring to electricity generated by hydropower. The production of electrical power through the use of the gravitational force of falling or flowing water. It is the most widely used form of renewable energy, accounting for 16% of global electricity generation, Euro 3,427 terawatt-hours of electricity production in 2010, and is expected to increase about 3.1% each year for the next 25 years. Hydropower is produced in 150 countries, with the Asia-Pacific region generating 32% of global hydropower in 2010. China is the largest hydroelectricity producer, with 721 terawatt-hours of production in 2010, representing around 17% of domestic electricity use. There are now 4 hydroelectricity plants larger than 10 GW, the 3 Gorges Dam and Xiluodu Dam in China, Itaipu Dam across the Brazil-Paraguay border, and Guri Dam in Venezuela. The cost of hydroelectricity is relatively low, making it a competitive source of renewable electricity. The average cost of electricity from a hydro plant larger than 10 megawatts is 3 to 5 US cents per kilowatt hour. It is also a flexible source of electricity since the amount produced by the plant can be changed up or down very quickly to adapt to changing energy demands. However, damming interrupts the flow of rivers and can harm local ecosystems, and building large dams and reservoirs often involves displacing people and wildlife. Once a hydroelectric complex is constructed, the project produces no direct waste, and has a considerably lower output level of the greenhouse gas carbon dioxide, CO2, than fossil fuel-powered energy plants. History. Hydropower has been used since ancient times to grind flour and perform other tasks. In the mid-1770s, French engineer Bernard Forest de Bar-Copyright published Architecture hydraulique, which described vertical and horizontal axis hydraulic machines. By the late 19th century, the electrical generator was developed and could now be coupled with hydraulics. The growing demand for the Industrial Revolution would drive development as well. In 1878, the world's first hydroelectric power scheme was developed at Cragside in Northumberland, England by William George Armstrong. It was used to power a single arc lamp in his art gallery. The old Sho-Elkopf Power Station No. 1 near Niagara Falls in the U.S. side began to produce electricity in 1881. The first Edison hydroelectric power plant, the Vulcan Street Plant, began operating September 30, 1882, in Appleton, Wisconsin, with an output of about 12.5 kilowatts. By 1886 there were 45 hydroelectric power plants in the U.S. and Canada. By 1889 there were 200 in the U.S. alone. At the beginning of the 20th century, many small hydroelectric power plants were being constructed by commercial companies in mountains near metropolitan areas. Grenoble, France held the International Exhibition of Hydropower and Tourism with over 1 million visitors. By 1920, as 40% of the power produced in the United States was hydroelectric, the Federal Power Act was enacted into law. The act created the Federal Power Commission to regulate hydroelectric power plants on federal land and water. As the power plants became larger, their associated dams developed additional purposes to include flood control, irrigation and navigation. Federal funding became necessary for large-scale development, and federally owned corporations, such as the Tennessee Valley Authority and the Bonneville Power Administration, were created. Additionally, the Bureau of Reclamation, which had begun a series of western U.S. irrigation projects in the early 20th century, was now constructing large hydroelectric projects such as the 1928 Hoover Dam. The U.S. Army Corps of Engineers was also involved in hydroelectric development, completing the Bonneville Dam in 1937 and being recognized by the Flood Control Act of 1936 as the premier federal flood control agency. Hydroelectric power plants continued to become larger throughout the 20th century. Hydropower was referred to as white coal for its power and plenty. Hoover Dam's initial 1,345 MW power plant was the world's largest hydroelectric power plant in 1936. It was eclipsed by the 6809 MW Grand Coulee Dam in 1942. The Itaipu Dam opened in 1984 in South America as the largest, producing 14,000 MW, but was surpassed in 2008 by the Three Gorges Dam in China at 22,500 MW. Hydroelectricity would eventually supply some countries, including Norway, Democratic Republic of the Congo, Paraguay and Brazil, with over 85% of their electricity. The United States currently has over 2,000 hydroelectric power plants that supply 6.4% of its total electrical production output, which is 49% of its renewable electricity. Generating methods. Conventional. Most hydroelectric power comes from the potential energy of dammed water driving a water turbine and generator. The power extracted from the water depends on the volume and on the difference in height between the source and the water's outflow. This height difference is called the head. The amount of potential energy in water is proportional to the head. A large pipe delivers water to the turbine. Pumped storage. This method produces electricity to supply high peak demands by moving water between reservoirs at different elevations. At times of low electrical demand, excess generation capacity is used to pump water into the higher reservoir. When there is higher demand, water is released back into the lower reservoir through a turbine. Pumped storage schemes currently provide the most commercially important means of large-scale grid energy storage and improve the daily capacity factor of the generation system. Pumped storage is not an energy source, and appears as a negative number in listings. Run-of-the-river. Run-of-the-river hydroelectric stations are those with small or no reservoir capacity, so that the water coming from upstream must be used for generation at that moment, or must be allowed to bypass the dam. In the United States, run-of-the-river hydropower could potentially provide 60,000 MW. Tide. A tidal power plant makes use of the daily rise and fall of ocean water due to tides. Such sources are highly predictable, and if conditions permit construction of reservoirs, can also be dispatchable to generate power during high demand periods. Less common types of hydro schemes use water's kinetic energy or undammed sources such as undershot waterfalls. Tidal power is viable in a relatively small number of locations around the world. In Great Britain, there are 8 sites that could be developed, which have the potential to generate 20% of the electricity used in 2012. Underground. An underground power station makes use of a large natural height difference between two waterways, such as a waterfall or mountain lake. An underground tunnel is constructed to take water from the high reservoir to the generating hole built in an underground cavern near the lowest point of the water tunnel, and a horizontal tail race taking water away to the lower outlet waterway. Sizes and capacities of hydroelectric facilities. Large facilities. Although no official definition exists for the capacity range of large hydroelectric power stations, facilities from over a few hundred megawatts to more than 10 GW are generally considered large hydroelectric facilities. Currently, only 3 facilities over 10 GW are in operation worldwide. Three Gorges Dam at 22.5 GW, Itaipu Dam at 14 GW, and Guri Dam at 10.2 GW. Large-scale hydroelectric power stations are more commonly seen as the largest power-producing facilities in the world, with some hydroelectric facilities capable of generating more than double the installed capacities of the current largest nuclear power stations. Small hydro is the development of hydroelectric power on a scale serving a small community or industrial plant. The definition of a small hydro project varies, but a generating capacity of up to 10 megawatts is generally accepted as the upper limit of what can be termed small hydro. This may be stretched to 25 MW and 30 MW in Canada and the United States. Small-scale hydroelectricity production grew by 28% during 2008 from 2005, raising the total world small hydro capacity to 85 GW. Over 70% of this was in China, followed by Japan, the United States, and India. Small hydro plants may be connected to conventional electrical distribution networks as a source of low-cost renewable energy. Alternatively, small hydro projects may be built in isolated areas that would be uneconomic to serve from a network, or in areas where there is no national electrical distribution network. Since small hydro projects usually have minimal reservoirs and civil construction work, they are seen as having a relatively low environmental impact compared to large hydro. This decreased environmental impact depends strongly on the balance between stream flow and power production. Micro hydro is a term used for hydroelectric power installations that typically produce up to 100 kilowatts of power. These installations can provide power to an isolated home or small community, or are sometimes connected to electric power networks. There are many of these installations around the world, particularly in developing nations, as they can provide an economical source of energy without purchase of fuel. Micro-hydro systems complement photovoltaic solar energy systems because in many areas, water flow, and thus available hydropower, is highest in the winter when solar energy is at a minimum. Pico hydro is a term used for hydroelectric power generation of under 5 kilowatts. It is useful in small, remote communities that require only a small amount of electricity. For example, to power 1 or 2 fluorescent light bulbs and a TV or radio for a few homes. Even smaller turbines of 200-300 W may power a single home in a developing country with a drop of only 1 am. A Pico hydro setup is typically run-of-the-river, meaning that dams are not used, but rather pipes divert some of the flow, drop this down a gradient, and through the turbine before returning it to the stream. Calculating available power. A simple formula for approximating electric power production at a hydroelectric plant is, where, is power in watts, is the density of water, is height in meters, is flow rate in cubic meters per second, is acceleration due to gravity of 9.8 ams2, is a coefficient of efficiency ranging from 0 to 1. Efficiency is often higher with larger and more modern turbines. Annual electric energy production depends on the available water supply. In some installations, the water flow rate can vary by a factor of 10 over the course of a year. Advantages and disadvantages. Advantages. Flexibility. Hydro is a flexible source of electricity since plants can be ramped up and down very quickly to adapt to changing energy demands. Hydro turbines have a start-up time of the order of few minutes. It takes around 60 to 90 seconds to bring a unit from cold start-up to full load. This is much shorter than for gas turbines or steam plants. Power generation can also be decreased quickly when there is a surplus power generation. Hence the limited capacity of hydropower units is not generally used to produce base power except for vacating the flood pool or meeting downstream needs. Instead, it serves as backup for non-hydro generators. Low power costs. The major advantage of hydroelectricity is elimination of the cost of fuel. The cost of operating a hydroelectric plant is nearly immune to increases in the cost of fossil fuels such as oil, natural gas or coal, and no imports are needed. The average cost of electricity from a hydro plant larger than 10 megawatts is 3 to 5 US cents per kilowatt hour. Hydroelectric plants have long economic lives, with some plants still in service after 100 years. Operating labor cost is also usually low, as plants are automated and have few personnel on site during normal operation. Where a dam serves multiple purposes, a hydroelectric plant may be added with relatively low construction cost, providing a useful revenue stream to offset the costs of dam operation. It has been calculated that the sale of electricity from the Three Gorges Dam will cover the construction costs after 5 to 8 years of full generation. Additionally, some data shows that in most countries large hydropower dams will be too costly and take too long to build to deliver a positive risk-adjusted return, unless appropriate risk management measures are put in place. Suitability for industrial applications. While many hydroelectric projects supply public electricity networks, some are created to serve specific industrial enterprises. Dedicated hydroelectric projects are often built to provide the substantial amounts of electricity needed for aluminium electrolytic plants, for example. The Grand Coulee Dam switched to support Alco Aluminium in Bellingham, Washington, United States for American World War II airplanes before it was allowed to provide irrigation and power to citizens after the war. In Suriname, The Brokopondo Reservoir was constructed to provide electricity for the aluminium industry. New Zealand's Manapuri Power Station was constructed to supply electricity to the aluminium smelter at Taiwai Point. Reduced CO2 emissions. Since hydroelectric dams do not burn fossil fuels, they are claimed to not directly produce carbon dioxide. While some carbon dioxide is produced during manufacture and construction of the project, this is a tiny fraction of the operating emissions of equivalent fossil fuel electricity generation. One measurement of greenhouse gas-related and other externality comparison between energy sources can be found in the Externe project by the Paul Scherrer Institute and the University of Stuttgart, which was funded by the European Commission. According to that study, hydroelectricity produces the least amount of greenhouse gases and externality of any energy source. Coming in second place was wind, third was nuclear energy, and fourth was solar photovoltaic. The low greenhouse gas impact of hydroelectricity is found especially in temperate climates. The above study was for local energy in Europe. Presumably similar conditions prevail in North America and Northern Asia, which all see a regular, natural freeze-thaw cycle. Greater greenhouse gas emission impacts are found in the tropical regions, the lower latitude regions of the Earth, as it has been noted that the reservoirs of power plants in tropical regions produce a larger amount of the greenhouse gas methane. Other uses of the reservoir. Reservoirs created by hydroelectric schemes often provide facilities for water sports, and become tourist attractions themselves. In some countries, aquaculture in reservoirs is common. Multi-use dams installed for irrigation support agriculture with a relatively constant water supply. Large hydro dams can control floods, which would otherwise affect people living downstream of the project. Disadvantages: ecosystem damage and loss of land. Large reservoirs required for the operation of hydroelectric power stations result in submersion of extensive areas upstream of the dams, destroying biologically rich and productive lowland and riverine valley forests, marshland and grasslands. The loss of land is often exacerbated by habitat fragmentation of surrounding areas caused by the reservoir. Hydroelectric projects can be disruptive to surrounding aquatic ecosystems both upstream and downstream of the plant site. Generation of hydroelectric power changes the downstream river environment. Water exiting a turbine usually contains very little suspended sediment, which can lead to scouring of river beds and loss of river banks. Since turbine gates are often opened intermittently, rapid or even daily fluctuations in river flow are observed. Siltation and flow shortage: when water flows it has the ability to transport particles heavier than itself downstream. This has a negative effect on dams and subsequently their power stations, particularly those on rivers or within catchment areas with high siltation. Siltation can fill a reservoir and reduce its capacity to control floods along with causing additional horizontal pressure on the upstream portion of the dam. Eventually, some reservoirs can become full of sediment and useless or overtop during a flood and fail. Changes in the amount of river flow will correlate with the amount of energy produced by a decommitter. Lower river flows will reduce the amount of live storage in a reservoir, therefore reducing the amount of water that can be used for hydroelectricity. The result of diminished river flow can be power shortages in areas that depend heavily on hydroelectric power. The risk of flow shortage may increase as a result of climate change. One study from the Colorado River in the United States suggests that modest climate changes, such as an increase in temperature in 2 degrees Celsius resulting in a 10% decline in precipitation, might reduce river runoff by up to 40%. Brazil in particular is vulnerable due to its heaving reliance on hydroelectricity, as increasing temperatures, lower water IO and alterations in the rainfall regime, could reduce total energy production by 7% annually by the end of the century. Methane emissions. Lower positive impacts are found in the tropical regions, as it has been noted that the reservoirs of power plants in tropical regions produce substantial amounts of methane. This is due to plant material in flooded areas decaying in an anaerobic environment, and forming methane, a greenhouse gas. According to the World Commission on Dams report, where the reservoir is large compared to the generating capacity and no clearing of the forests in the area was undertaken prior to impoundment of the reservoir, greenhouse gas emissions from the reservoir may be higher than those of a conventional oil-fired thermal generation plant. In boreal reservoirs of Canada and northern Europe, however, greenhouse gas emissions are typically only 2% to 8% of any kind of conventional fossil fuel thermal generation. A new class of underwater logging operation that targets drowned forests can mitigate the effect of forest decay. Relocation. Another disadvantage of hydroelectric dams is the need to relocate the people living where the reservoirs are planned. In 2000, the World Commission on Dams estimated that dams had physically displaced 40 to 80 million people worldwide. Failure risks. Because large conventional dammed hydro facilities hold back large volumes of water, a failure due to poor construction, natural disasters or sabotage can be catastrophic to downriver settlements and infrastructure. Dam failures have been some of the largest man-made disasters in history. The Bangye Dam failure in southern China directly resulted in the deaths of 26,000 people, and another 145,000 from epidemics. Millions were left homeless. Also, the creation of a dam in a geologically inappropriate location may cause disasters such as 1963 disaster at Vajont Dam in Italy, where almost 2,000 people died. Smaller dams and micro-hydro facilities create less risk, but can form continuing hazards even after being decommissioned. For example, the small Kelly Barnes Dam failed in 1967, causing 39 deaths with the Toko flood, 10 years after its power plant was decommissioned. Comparison with other methods of power generation, hydroelectricity eliminates the flue gas emissions from fossil fuel combustion, including pollutants such as sulfur dioxide, nitric oxide, carbon monoxide, dust, and mercury in the coal. Hydroelectricity also avoids the hazards of coal mining and the indirect health effects of coal emissions. Compared to nuclear power, hydroelectricity generates no nuclear waste, has none of the dangers associated with uranium mining, nor nuclear leaks. Compared to wind farms, hydroelectricity power plants have a more predictable load factor. If the project has a storage reservoir, it can generate power when needed. Hydroelectric plants can be easily regulated to follow variations in power demand. World hydroelectric capacity. The ranking of hydroelectric capacity is either by actual annual energy production or by installed capacity power rating. Hydro accounted for 16% of global electricity consumption, and 3,427 terawatt-hours of electricity production in 2010, which continues the rapid rate of increase experienced between 2003 and 2009. Hydropower is produced in 150 countries, with the Asia-Pacific region generated 32% of global hydropower in 2010. China is the largest hydroelectricity producer, with 721 terawatt-hours of production in 2010. Representing around 17% of domestic electricity use. Brazil, Canada, New Zealand, Norway, Paraguay, Austria, Switzerland, and Venezuela have a majority of the internal electric energy production from hydroelectric power. Paraguay produces 100% of its electricity from hydroelectric dams, and exports 90% of its production to Brazil and to Argentina. Norway produces 99% of its electricity from hydroelectric sources. There are now 3 hydroelectric plants larger than 10 GW, the 3 Gorges Dam in China, Itaipu Dam across the Brazil-Paraguay border, and Guri Dam in Venezuela. A hydroelectric plant rarely operates at its full power rating over a full year. The ratio between annual average power and installed capacity rating is the capacity factor. The installed capacity is the sum of all generator nameplate power ratings. Major projects under construction, see also. Hydraulic engineering, international rivers, list of energy storage projects, list of hydroelectric power station failures, list of hydroelectric power stations, list of largest power stations in the world, XCEL Energy Cabin Creek Hydroelectric Plant Fire, references. External links. International Hydropower Association, Hydroelectricity at DMOZ, National Hydropower Association, USA, Hydropower Reform Coalition, Interactive Demonstration on the Effects of Dams on Rivers, European Small Hydropower Association, IECTC4, Hydraulic Turbines IECTC4 portal with access to scope, documents and TC4 website.